Okay, so we have an example of exponential growth here when we did the paper folding activity. When we had 0 folds, there was 1 section. When we had 1 fold, there was 2 sections, 2 folds, and 4 sections, and so on. But now I want to look at what happens if we swap the X and the Y on all of these ordered pairs. So if we wanted to swap the X's and the Y's, and I'm just going to go ahead and draw in this exponential here. If we're doing some curve fitting and trying to see which type of curve fits it best, the exponential would fit it best. A straight line wouldn't cut it, even a parabola or a U shape. The quadratic isn't a good fit. A straight line's not a good fit. A circle's not a good fit. It's this exponential is a good fit for that data. But now let's look at what if we swapped all of these X's and Y's here. And see what the graph would do. So let's say we had, instead of 0 sections, 1 or 0 folds 1 section, we'll put it in as a 1, 0. And then instead of 1, 2, we'll put it in as 2, 1. And then this one would be 4, 2. And the next one would be 8, 3. And the next one would be 16, 4. You see the pattern that is emerging here is the inverse of that exponential. And we call this a logarithmic function. So you can see how it's just a swap. It just reflects right across this line right here. If you fold it across this line, you get the log. So it's really cool how this real world data is just a sheet of paper folding over and over. That application shows us the exponential growth versus the logarithmic growth. It's growing, but not very fast. And that was from when we got our scatter plot of the paper folding. Would anybody like